Okay, good afternoon, guys. Yeah. Oh yeah, so yes, the first thing I wanted to tell you that I am kind of like proposing a date for exam 2. And the date I have in mind is Monday, April 12th. And the timing will be like the same. It'll be from 12 to 12. Okay. And the topics will be assignments 4, 5, and 6. And I'll post assignment 6 today. Assignment 6 will just be about a few questions, like 1 or 2 questions about cardinality. Okay. So try them. So roughly assignment 4 is like about arithmetic of natural numbers. Assignment 5 is kind of like about some things about real numbers. And assignment 6 will be cardinality, roughly. Okay. So that's kind of the topics that you'll see on the exam. Okay. As some of you are also in Math 3272. Oh, will we have our 2-hour class that day? That is a good question. Well, I guess my question in response to your question is, I guess there's like 2 options. Here's option 1. Would be to have it on Tuesday, a Tuesday exam. My only thing is that moves it 1 day closer to what I understand is another exam you have later. So I'd rather, I mean, that is an option, but maybe, okay, anyways, that's one option. Option 2, I could just kind of work on 2 hours of videos. Well, not exactly 2 hours, like an hour and a half of videos to watch at whenever is convenient for you instead of that class. I was already planning to do that for the Easter Monday class anyways. So it wouldn't be so good to do that twice in a row, but that is the other option. Option 2. Well, I don't know if this is fair, but is anyone really opposed to option 2? Okay. Yeah. I guess maybe the people who aren't here, they'd also prefer option 2 because they might end up just watching it at a later date anyways. So I guess it's not so unfair. So yeah, let's just go with option 2. So the exam will say here. And I'll do that. Okay. And now that it's come up, no, we'll have no class on Easter Monday. Well, I think it's a holiday, right? So once it's a holiday, we won't have any class then. But videos instead. Okay. Because I can't really give up the 2 hours entirely. Okay, so does anyone? No. Where is this? Okay. So that is what will happen. Also, just for your information, I'm like about halfway done marking. I should be done very soon. Well, today. Okay, so just check tomorrow if you want, and you should be able to find out what's happening with the first exam. Okay. Okay. Right. Okay. Oh, and I forgot it, because I was going to mention this. I know some of you guys are in abstract algebra 2. So I wanted to put that exam. I'll post this information to abstract to manual learning, but I can just tell you that will be actually that will be I want to put that exactly 2 weeks from today. So that'll be April 7th. And then the topics would be just assignments 4 and 5. This is in 2 weeks. That's 2 weeks. Okay. Okay. Okay, so today I just want to kind of wrap up cardinal arithmetic. The idea is that, we've defined how to add cardinalities and multiply them, and we can say that one cardinality is less than or equal to another and stuff like that. And we just want to prove a few basic properties. Okay, so let me state some of the properties. We proved one as an example. We proved it, like we proved that kappa plus kappa equals 2 times kappa as an example. And I just maybe want to do a couple more examples like that. To wrap things up. Okay. So this is on cardinality. Okay, let me remind you what the definition of cardinality is, like addition of cardinals and so on. So as long as kappa is the cardinality of A and lambda is the cardinality of B, and A and B are disjoint, then we can define the cardinality of kappa plus lambda. Sorry, we can define kappa plus lambda as just the cardinality of A union B. And if A and B are not disjoint, we just replace them by 2 sets of the same cardinality, which are disjoint. So that's in general how we do things. And then kappa times lambda, well, that's just the cardinality of the Cartesian product. Kappa to the power lambda, well, that's just the cardinality of the set of all functions from B to A. Let me remind you that A to the B, that's all the F's from B to A. Okay, and you notice like some nice, I don't know, some nice interaction between multiplication of cardinals and the Cartesian product, the exponentiation of cardinals, and like this exponent. That's why we choose these like ways of defining cardinal arithmetic. I guess you could also say like you could define 2 to the lambda to be the power set of B if you wanted. And other things. Okay, so let's let's try and prove some of the basic properties for these like for cardinal arithmetic. Proposition. For addition, we have a left knot plus a left knot equals a left knot. Okay. We have kappa plus lambda is lambda plus kappa. We have kappa plus lambda plus mu equals kappa plus lambda plus mu. We have kappa is less than or equal to kappa plus lambda. Then we have a kind of inequality. Okay, so let's maybe prove this one. And let's do like another one. I mean, the rest of them are all kind of similar. They're not like that bad, but I guess let's just sit, we can do this one, I guess. Okay. Okay, so the first thing is essentially saying that the union of two countable sets is also countable. Okay. One says if the cardinality of A is the cardinality of the natural numbers, and cardinality of B is also cardinality of natural numbers, then cardinality of A union B also equals the cardinality of the natural numbers. Okay. So one way to do this is to write A as A0, A1, A2 to AN and keep on going. And write B as B0, B1 to BM and keep on going. And now let's define a one-to-one and onto function from the natural numbers to A union B, and let's assume like A intersect B is just is the empty set. Okay, and define F from the natural numbers to A union B to be F of n is going to be, what should it be? I guess A sub n over 2 if n is even, and it should be A sub n minus 1 over 2 if n is odd. And let's just make sure that, oh, sorry, it should be B of that. Okay. And let's just make sure that it's not crazy to do that. So this says like F of 0 should be A0, F of 1 should be B0, F of 2 should be A1, F of 3 should be B1. So we just go like this. We count them off like A0, B0, A1, B1, A2, B2, A3, B3, blah, 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 like that. We alternate. Okay. This is definitely 1-to-1, just because by assumption, like these are all distinct. And these are all distinct, and the two sets are disjoint. I guess if they're not disjoint, it's not necessarily 1-to-1. Well, that's why we assume they're disjoint. Okay. And it is also onto, because we assume that we've enumerated all the elements of A, like as this, and same for B. Okay, so I guess we should just say now, note that F is 1-to-1 and onto. So that tells us that A union B is also countable. Okay. And a similar proof kind of proves that it proves that any finite union of countable sets is also countable. Like we can, like, these are kind of fun exercises. Prove that if A1, A2 up to AN are countable, and so is A1 union A2 AN, and also you want to assume that AI intersect AJ is the empty set if I is not equal to J, things like that. So a finite union of countable is countable. I think you can also prove countable union of countable is countable. You can do the same thing for Cartesian products. As we saw. Okay. Okay. We can write down another proposition and kind of, you can say a lot of the same things except for multiplication of cardinals. Let's see, kappa times lambda is lambda times kappa. You have kappa lambda mu is kappa lambda times mu. You have kappa times lambda plus mu. That's just kappa lambda plus kappa mu. If lambda is strictly bigger than the empty set, then kappa is less than kappa lambda. Oh yeah, and then we have kappa plus kappa, which we already proved, 2 times kappa. Okay, so like, you know, we could do like maybe this one, just to see what the kind of argument we would use. Proof of this one. Okay, so right, kappa. Oh yeah, I said I was gonna do that kappa plus lambda equals lambda plus kappa. Let's just do this one instead. Yeah, okay. Hope that's okay. So so kappa, lambda, and mu are cardinalities. So they're going to be the cardinalities of sets A, B, and C. And if we're going to assume that B intersects C is disjoint, if B intersects C is not disjoint, we're going to replace B with like a B prime with the same cardinality that's disjoint from C. It's just like replace it like it's just like a little trick or something, like take all the elements of B and like change them slightly, like color them all purple or something. And now they're all different from what they were. So if they did intersect with C, now they don't, I guess. And you can do it in a way that is mathematically precise and not coloring purple. But yeah, we're just going to assume that B intersects C is empty. Okay. Now, the definition of these two cardinal, we'll write down the definition of these two cardinalities. Okay. First, kappa lambda, that's the cardinality of Cartesian product of A and B. Kappa mu, that's the cardinality of the Cartesian product of A and C. And notice this Cartesian product, these two Cartesian products are disjoint since B and C are disjoint. Like if any ordered pair was in both of these, they would have the same second coordinate. That same second coordinate would be an element of B and C, but that's not possible. Okay, so therefore, kappa lambda plus kappa mu, that's defined to be the cardinality of A times B union A times C. Now, kappa times lambda plus mu, that's defined to be the cardinality of A, Cartesian product of A with B union C. Okay. And now something funny happens. Well, this set and this set are exactly the same. This doesn't always happen for all the different ones. Okay. So this set equals this set. Well, that means they have the same cardinality because they are the same. Okay. But it's so these two cardinalities are actually equal to the cardinality of some sets, so these two cardinalities are equal. Okay. Implicitly, we have used the fact that the cardinality of A equals the cardinality of A. Or rather, I guess what have we used? No. I'm actually not sure if we use transitivity or reflexivity, but we use something anyways. Okay, just one more example. Let's just show, like kappa lambda equals lambda kappa. Okay. Oh. So lambda is going to be the cardinality of B, kappa the cardinality of A. And we're going to construct F from A cross B to B cross A by mapping A comma B to B comma A. Okay, this F is clearly one-to-one and onto. One way to see that is, well, the inverse is just to take BA and turn it into AB. You know, or you can directly prove that this map is one-to-one and onto. Okay, and that shows that cardinality of A times B is the same as the cardinality of B times A. Well, that's just kappa lambda, and on the right-hand side, that's just lambda kappa. Okay, so that is usually how things work out with this. You find some like one-to-one and onto function between the representatives of the sets you're trying to define the cardinality for. Okay. And we can the last thing I wanted to do was to restate Cantor's like diagonalization argument. It's in a more general setting. A theorem. Okay, let X be a set. Then the cardinality of X is strictly less than the cardinality of the power set of X. Proof. We'll prove this. Wait, actually, let's take like 3 minutes. Then when we come back, we'll do this proof and that'll be the last thing we do for today. Okay, sorry for the interruption. I just don't feel like I'm gonna finish this before my 40 minutes is up. Okay, so yeah, just take, I'll start back up in 3 minutes.